All right. How we doing? Great. Make sure we're recording here. Awesome, neat, cool. Okay, folks. Love the shirt. Oh my goodness, the official. I see this. This is the official. This is the first time I'm seeing it in person. I was. Yes. Oh, look at the size. Is good. This is good.
All the
All right. Good. Yeah. How about that? Good. Translated well. Awesome. Thank you. Thank you. Yeah. Thank you for supporting the Robotics Education Fund. All right. To be clear, no extra credit is earned from purchasing merch. Just make it absolutely clear. All right. So today it's our last official in-person lecture for the term. Boo, 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 boo. We want more lectures. Well, you know, one thing actually I look forward to the summer is I used to just randomly just pop on Twitch and do lectures and just on random things. And, during the summer I don't have teaching, so it's a good opportunity to try some things. So, stay tuned to the YouTube channel if you want to check out me rambling about whatever. So anyway, so hope you're all doing great. So let's touch base a little bit today just on some end of term stuff. Okay, so end of term housekeeping, all right? So there's only 2 assignments left in the works. One is the optional recovered credit homework assignment on reinforcement learning that's been posted, okay? And the other is the project, both of which are due at the end of finals week, okay? Those are the only 2 remaining components of the class that we've not finished, all right? So just to cover a couple bases here. All right. Here we go. All right. So today, my goodness, the 21st of April. Okay. So today's going to be our last in-person lecture. Okay. Next lecture, Thursday, is a project workshop. Okay. Gives you an opportunity to be here. TAs will be here to work with you on your projects, okay? So it'll be here in person. So I highly encourage everyone to be here with your project teams because this is your chance to talk to to talk to some experts here, okay? I just play one on TV. They know how to help you. No, so some folks have been coming to the office hours and showing me their preliminary results for their neural network. And I was like, oh, that looks good. Let's try this. And then you learn something from trying that. Like, oh, maybe it's not working as well as I thought. That's normal. That's part of the process. The likelihood that you just at the last minute throw this together and it works, you're like, oh, great, awesome, it works, is fairly small. Happened. Weirdly, it's happened to me during lecture. I've just randomly put things together and they somehow worked. But that's a different story. I have some experience in the matter. All right. So anyway, so Thursday, project workshop. Now we should have all of your project updates. They were due yesterday, so we have something that the TAs can look at. All right. So they can pull that up and talk to you during the session. So in class, and specifically in here, in AME 106. All right. And also, I find it's a good opportunity to have your whole group there. Also, you can talk with each other when they're not talking to you, okay? So I find that that's a useful thing, just putting you all in the same space, all right? For the final project, there are some details. They've been posted online in terms of the format of the final project report, okay? There's a Word document. If you wanted to do your own LaTeX version of it, sure. Anyone know what LaTeX is? Who here knows about overleaf? Everyone? What do you learn about overleaf? A variety of things. You learn about overleaf? I didn't learn it until I was a PhD student about, well, we didn't have overleaf. We just had LaTeX without overleaf. We had to like compile it with commands. It was just hard, probably because I was trying to type like this. That was probably the main issue. But so there's a Word doc format. If you want to convert that into a LaTeX version of the format, because you like LaTeX equations, who doesn't? But you can use that too. Oh, sorry, what's that, sir? Yeah, well, LaTeX is way better for equations. It's well, okay, my friends. Just since we're all getting on our high horse about equations and LaTeX, okay, who here uses PowerPoint? There are people who don't use PowerPoint. Okay. Well, there's LaTeX versions of PowerPoint.
Yeah, what? Yes. Yes, there are. I think it's called Beamer. I think it's only because I'm panicking in the moment. I forgot it's been so long. I never use it because I like my animations too much in PowerPoint. But like, you go to like a more mathematically themed talk, it's all in Beamer, and they can just paste in their equations into this LaTeX format. It's great. There are LaTeX versions of like drawing called ticks and things like that, where you can, anyway. I like to draw old-fashioned with a, I was going to say with a pencil. I meant with a mouse and clicking, but that's just me. So there's a Word document format. There's a video, approximately 5 minutes. Okay. Again, it's never been easier. You can hop on a Zoom call and you can record the Zoom call. But what I recommend you do is we have to send a link that we can view it at. Easiest thing, just take one of you, if you have a Google account, upload it as an unlisted YouTube video. It can be listed if you want, that's fine. Unlisted means it's just not searchable, in case you want this to not, mess with your analytics for, for your YouTube monetization, whatever you're doing. Okay, so you can list as an unlisted YouTube video. That way you can get to it if you have the link. Okay. That way it doesn't mess with your unboxing videos or whatever was popular in 2012. Okay. All right. Okay. So that's it. That's due last day. So that's Friday finals week. Okay. Now I will be having office hours during finals week as well. Okay. I'm going to send out an announcement that I don't have office hours tomorrow at the exact same time. I need to shift my office hours tomorrow, but I'll be having other office hours this week, and I'll be having 2 office hours next week as well to help with your projects. So I am around, and like I say, if you're struggling, go to office hours. It's shockingly lonely. I went on TV so people would want to talk to me in office hours, and I have mostly failed. Mostly failed. Okay, so point that out. Okay, so office hours, for the TAs will be around as well. It's all available for you, my friends. All available. So, okay. Any questions about things we're finishing up the end of the term, about projects, about the homework, optional? Homework can't hurt your grade. It only help your grade. That said, you have to make a real good attempt if you're going to want to get points back. Okay, you can't just do a half-hearted attempt and expect to get points back from your previous assignments. Grading scale, I believe, is up on the assignment. Okay, awesome. No other questions. Okay. Okay. This is all bonus material at this point, right? You're here because I require you to be, but other than that, you're here to learn. Okay, and I like to think we covered a lot of stuff this term. Okay. Not all of it was covered in the homeworks. That'll be way too much. Hopefully you've absorbed that material. That material will always be online for you to reabsorb whenever you want. Okay. Also, I had a request, and I apologize I did not get back to you. I will try to get up those, like the lecture notes. So thank you for your patience with those. I know people wanted the lecture notes. It's a lot of processing on my end, but I can get it up. I really wanted to get it out there. And hopefully in a more permanent form than Canvas as well, because when eventually you don't have your logins anymore, you don't have Canvas anymore. We don't want that. So I'll have to find some way to get that up onto, like, I don't know, my website or something where it's always available. That's what the summer is for. But we've covered a lot of different topics. Let's just review. What have we covered? Okay. We talked about, machine learning in general. So this course. Talked about machine learning paradigms. We covered supervised. Unsupervised, where you don't have labeled data. You're just coming up with structures. Okay? Supervised was things like regression or classification, where we had the images. We're like, is that a picture of a 1, a 2, or 3, or 4? We coded it ourselves. We trained a neural net. Say, here's the image. What is it? It's a 3. Good job. Okay? We did that. That was supervised. All right. We also have unsupervised. We did a very brief little clustering algorithm. We did a k nearest neighbor clustering, where we tried to do little. This was a cluster, and that was a cluster. We coded that up real quick. But also we talked a little bit about autoencoders, which were like dimensional reducers. The idea is that they are neural nets that the only job they have is to take in the input, that out of it comes the same thing. What? But in the middle, there were fewer nodes, and this was last lecture, a week ago. Yes. Yesterday. Oh wait, Thursday. There were fewer nodes and there were fewer neurons in that middle layer, so it had forced it to reduce the amount of information. Okay, so it basically forced you to capture the most important parts of your input. So if you have like a noisy signal, you have like a noisy image with lots of just scattered little dibbity dots in it, it can help get rid of that information. Okay, and reduce the dimensionality. That's what unsupervised was. We also talked about reinforcement learning. Okay. RL, we spent a number of lectures on that, where you have a reward, you have an agent that's interacting with an environment to come up with a policy. It's getting a reward signal. Good reward is good. Low reward is bad. Okay. We covered we covered different versions of those things. We talked a lot about gradient descent, which is our algorithm, which is our typical optimization algorithm. We did stochastic gradient descent, and we did this ourselves. We coded up in class, and you coded up in your homework, your stochastic gradient descent. And we did momentum-based gradient descent, GD, and a special version of it, which had a second momentum term, called atom. We coded that all from scratch. It's all there. We did it every single line. Okay? We had gradient descent optimization. We also covered neural networks and deep neural networks. They're just neural networks with more layers. Okay? The more layers you have, the more deep the neural networks are, where you have all your weights and biases. We started off with feed-forward neural networks. That's where you have an input, then it becomes an output on the other side. We mostly dealt with feed-forward neural networks. The most common of which was the multi-layer perceptron, or the MLP. That's where you have an input, you have lots of little hidden layers. They're all fully connected up like that. It's dense and fully connected. Okay. And then for images, we covered something called the convolutional neural network. And that was for things like images, or when you have gridded information, whole grids of information. And that's what we used to identify those pictures of numbers. Like, oh, here is a 1. That equals 1. That's what we did for our examples, right? Okay? It's sort of like an overview of the things we covered in this class, all from not knowing maybe anything about machine learning or very little about Python. Okay? I do want to cover at least one other, so what I'm trying to highlight here is there are lots of little bits of things that we covered. We covered different types of activation functions. You know, those are your swishes, those are your tan-h's, those are your ReLUs. We covered things like normalization. That's when you just make the numbers stay within a certain range. Normalization. That's really important. It was really important for your homeworks that you did normalization. You can do mean standard deviation normalization, so you have a standard deviation of 1 with a mean of 0. That's totally cool. You just, again, it's just like subtracting and dividing numbers. It's like not the hardest thing ever, right? There's also this thing called regularization, which sounds a lot like normalization, but that's all about overfitting, trying not to overfit. We had these techniques such as early stopping. Where you realize that, hey, I'm starting to overfit, stop training. Okay? There are also regularization terms that you could add to your cost function. So you could have terms, such as some lambda w squared that more or less says, hey, penalize when you have large weights and biases. That means you're probably making very strong assumptions about your data. Don't do that. Make them smaller. Anyway, those are regularization techniques. Okay? All of these are important concepts in modern machine learning and machine learning in general. Okay? And it all started off with linear regressions, Okay. Love the shirt again. Okay. Loving the shirts. Okay. I do want to talk about one last type of neural network today. Just to give you a bit more of just something you've seen, so you've seen it. If you see it out in the world, people talking about it, you're like, I know what that is. And then with all the information that we're learned, we're going to go through a paper, like a real machine learning research paper that was written. They're all over the place. You literally just Google all over the place. They're often on the archive, but pronounced archive. Yeah, that's where lots of people put their papers for free to read for free. Okay, not for just machine learning, but for mathematics, for science, all over the place. The only thing I will say that on the archive, those papers have not necessarily gone through peer review yet. An expert hasn't looked at them and said, experts haven't looked at them and say that's good enough. Let's publish it in a journal or at a conference. Okay, but you can read a lot of papers there. Okay, just beware. All right. So we're going to go through a paper that was on the archive, and we're going to see how much of this paper we understand from what we've learned in class. It doesn't mean you have to understand every word, but can you follow along? Like, oh, I get what it's doing. Okay, what is that doing? What's that doing? What's the problem it's trying to solve? So we'll go through a real paper on that. Okay. So the last quick topic, we're going to talk about recurrent neural networks. Okay? Okay. Okay. Now, recall our convolutional neural networks. The whole job of those was to take grids of data and sort of and then collapse them together. We had these kernels where we'd say, oh, we have a bunch of pixels. Now let's do a thing where we take the maximum of a group of them and then shrink it down, shrink it down, shrink it down. That way we can get the information kind of bottled up. That's how we did all of that image classification. That was a convolutional neural network. It's good for dealing with grids, things like images. Or let's say if you're looking at, I don't know, weather radar data. You're looking at the weather and there's like, look at all these pixels where you have, oh, that's the green scary cloud on the radar. This is the white less scary cloud there. You look at all that data and the convolutional neural network has a way of encoding that information efficiently in a neural network. And the way that it got away with it is it had not all the weights were all different. Some of the weights were tied together to be the same way. You can go back to the lecture on convolutional neural networks to remind yourselves. But the point is, it was designed to be for things like gridded data. Okay? Recurrent neural networks are structured to be very good with sequential data. Okay? These are the networks that are designed for processing sequential data. What's a good idea? What's an idea of like sequential data? Well, I'll give you an example. Let's say just the position. Apologies for those who are in optimal control. I'm going to use the same example. I'm going to toss this thing around. The position of this thing over time. time 1, time 2, time 3, time 4, I'm tossing it. And where it ends up next is dependent upon where it was before in the sequence. It's dependent upon its previous state. There's a sequence of positions for this thing. So if you wanted to model this as a neural network, or you could use a recurrent neural network that takes into account this was the previous value I was at, what's the next value I was at? You could try to do this for the stock market. What's the stock market price now? Well, what was it just before? And the time before that? And the time before that? This is not financial advice, to be clear. Do not take your class project and if you invest based upon your class project, don't blame me, okay? Stock markets are famously volatile and hard to predict, okay? Or weather. If you haven't tried to predict the weather, well, is it dependent in any way on what the weather was yesterday? No? Not? Yes, I heard yes. Okay, I thought I heard, sorry, I'm hearing voices. That's a good sign, right? Okay. It's been a long semester. All right. Yeah, it can be dependent upon the weather yesterday. So if there's any dependence upon the sequence, maybe you want to use a recurrent neural network. Okay. So the idea of a recurrent neural network is imagine, imagine you are trying to predict the next data point in a sequence based on previous data in the sequence. Here's a killer example. Text prediction. Autocomplete. If your phone's going to suggest that next word in the sequence, it needs to know what the previous word was. And it might need to know multiple previous words. You know, I had Taco Bell, so I ran to the toilet. That's a good one. That required a lot of words in that sequence. Okay? So how would you create a neural network? Well, to predict that? Well, what data is being inputted into this sequence? Well, what you could do is you could have I ate Taco Bell, so I ran to the... These could all be some kind of inputs to a neural network. I'm not getting that Taco Bell sponsorship now, by the way. That ship has now sailed. Sorry to say. These could all be inputs to a neural network. You can't see that. All right. So imagine you have all these inputs to some fully connected neural network with all these neurons. And however, this is encoded as numeric data. Okay, it could go through some layer, right? Some fully connected network. Let's just treat this as an MLP, the multi-layer perceptron, okay, that we talked about previously, right? You have all of these. Okay, I'm getting lazy with my full connectedness, but you see what I'm doing. I'm connecting. Good. Thank you, Alan. Glad you agree. Okay? And then you'd have some prediction that comes out. Toilet. Okay? Right? If I want to have more history of these words, like I need to know all the way back to Taco Bell, that's probably important information to know what I'm running to, right? If I want to add more words, I got to add more inputs to my neural network, and probably a larger neural network that's going to need to process them all. doesn't scale up very well to trying to understand what you're trying to auto-predict. I mean, maybe it works to a degree, all right? But what if instead we had a recurrent neural network? The idea of a recurrent neural network is that, yes, you'll have some input X, and we're going to, and this current input, it goes into some activation of a hidden layer H, okay? But this, and instead of going to some output, I'm gonna erase this in a second, okay? It's going to loop back onto itself, okay? So this is some activation of some hidden layer. Then it's going to output to itself. And yes, you could read the output here and see what it's doing, right? But the next time you put in your next input, this hidden layer now has two inputs. Your new input and the result of your old activation, okay? Remembering what happened on the last iteration, okay? And that's now input to this current iteration. So what this would look like if you were to look at this over time, it's the equivalent of saying, hey, x at t minus 1, your input, goes into some neuron, which then goes into some neuron in the future, which has some new input xt, which then goes into some new neuron with some xt plus 1. So each of these are different times you actually run the neural network, okay? So this is going to be, call this ht minus 1, this is ht, this is ht plus 1. And that's plus 1 right there, I'm sorry. So the idea is that this neural network is dependent upon the output of the last time you ran the neural network. Okay? And this allows you to encode time series data, meaning a sequence of data, in a much smaller neural network with far fewer weights and biases to tune. Okay? So the RNN, the recurrent neural network, uses previous outputs of the hidden layers as inputs to future evaluations of the hidden layers. So it kind of loops. So in a similar way that when the convolutional network, that was with the image-based ones, we found clever ways to make the problem simpler by binning the data down into these little boxes, and then tying a lot of the weights together so a lot of the weights are the same and things. Recurrent neural networks simplify the problem by just saying, hey, we're just going to do this sequence of commands, and it's going to be the same activation function, and we're going to have the same weight here. We're going to keep using it over and over again over time. Keeps the network small, okay? This is a good way to do sequence modeling. So a sequence modeling neural network is often a recurrent neural network, okay? So, and to be clear, there's a lot more, you can make a much more complicated much more complicated recurrent neural networks than this. This is from these are all from the Goodfellow textbook, okay? So let's say you start with some input X. It's going to go into our recurrent hidden layer, okay? And it's going to loop onto itself, okay? right? And it's going to go to some output. We're going to call O. There's output. It's going to go to some loss function, or loss. Okay. And here, and this is going to be the, yeah. So anyway, there's our loss function. Okay. All right. Then what we do is you want to understand what this neural network looks like as you run it over and over and over again. We call it unfolding it. Okay. Here's xt minus 1. I'm going to write them before I put circles around them. I'm going to learn this lesson 8 years into being a professor. T plus 1. Going to go into ht minus 1, ht plus 1, okay, which goes into our various outputs, t minus 1, ot, ot plus 1, arrow, 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 and here's our loss, t minus 1, lt, lt plus 1. I'll draw my circles. T, that's t minus 1, that's what it says. Okay, lt. And cleverly, because this is the thing that's recurring, the graph of the neural network, all the little flow chart of it, has these hidden layers feeding into each other. So you're kind of emergently making this a more complicated neural net that's good for sequencing, okay? And that's what an RNN is, all right? Now, there are issues with this. You have to deal with the fact that if you get a big enough neural network, there's going to be at some point, the gradient of what happens way back, because you can do backprop on this. You can get the gradient using back propagation, just like everything else in neural networks and machine learning, okay? There are practical issues of this with how it remembers data. So people have come up with long and short-term memory, or LSTM networks. There are versions of recurrent neural networks that specifically cordon off. There's a long-term memory and a short-term memory that helps deal with some of these problems with gradients that emerge. You can compute them, but sometimes they become small and vanishing. Okay, but that's what LSTM stands for. Okay, a long-term, short-term memory. It's a type of recurrent network where it's remembering things through the recurrence of the network. Okay. All right. So we don't have time to code this up today. But I wanted to give you, and there's a whole, sorry, fine. Put that on Do Not Disturb. Okay. Sorry, that was Jeff Probst. That's all right. He's got a Tallahassee area code, as we all know. So all right. All right, got that. So, long-term, short-term memory, what we've got. So, I wanted to introduce you to this idea of recurrent neural networks and sequence modeling. There's a whole chapter on them in the Goodfellow text you can go through, okay? But that's the really short version of it. And if we were coding it up, we would just do it in Keras. We would just do it in Keras just like we did everything else, okay? Just to get it started for sequence modeling. Okay, but with that, I want to test our mettle today. Like, what do we know and understand about modern machine learning, and what's applied to a real modern machine learning paper? Okay, let me pull up this paper. Yeah. Here we go. Here's a paper. You want to Google it? It's called "Attention is All You Need," is the name of the paper. All right, it's a fancy titled paper. They're not all titled so fancily. Okay, it's a neat one. Okay, this one was co-authored by a lot of people at Google. You know, they do a lot of machine learning work. This is back from 2017, this paper. I know, no one was alive back then. No one was alive in 2017. All right? Okay, let's see. Let's see what we can understand. We're going to skim through this paper, see if we can catch the main drift of what's going on. And sorry, actually, you can't see it up on the, sorry, here we go. Called Attention is All You Need. It's the name of the paper, okay? All right, I just downloaded it to my iPad. You can find it online for yourself to Google through, okay? Do by a lot of these folks from Google and people from the University of Toronto, okay? One thing you'll notice that's really cool, I'm not sure if I can circle very well, that there's a little asterisk on the paper right there. They're like, we all contributed equally. It's a very nice thing. That's when everyone gets along. They're like, we like this paper so much. We all contributed equally. It's a nice thing that they said about each other. So, all right. So, what is this about? The dominant sequence transduction models, sequence modeling, thing we just talked about, okay, are based on complex recurrent neural networks and convolutional neural networks, things we talked about, some of which we've implemented. Okay, we understand what's going on. So we're talking about sequence modeling, okay? They include an encoder and a decoder, all right? An encoder and a decoder we talked a little bit about last lecture with the autoencoders, okay? But there are more types of encoders out there. Here we go. The best performing models, let's see, I wish I can I do this? I would like to be able to draw on this thing. Anyway, I'll try to like zoom in. I'll make it like a picture book. You know, it's actually like one of those it's like one of those YouTube shorts where the words pop up one at a time. It's what it is like. Performing models also connect the, okay, you're gonna get dizzy. All right, also connect the encoder and decoder through an attention mechanism. So this is about attention, something called an attention mechanism, okay? We propose a new simple network architecture called the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely, meaning we don't use recurrent neural networks. We don't use convolutions. We're using this thing called a transformer that has something called attention. All right, we don't understand fully what this is all about, but that's what this is the gist of it, okay? All right, we experiment on two machine translation tasks. So it's like translating language from like you know, French to English, okay? Shows that these models are superior in quality while being more parallelizable and requiring significantly less time to train. We know about training. We would click train and go on our network, on our code, right? And we'd train for a while, right? Okay, maybe we want to train in less time. And parallelizable, what do they mean by parallelizable? Anybody? They work in parallel. You can put them on GPUs and do them all, and that way you don't have to do them all in a row on a CPU. So they'll train faster, okay? That's what they're talking about, including ensembles over two blue. We'll figure out what blues are. Anyway, they have English to French translation tasks, and they establish a new single model state-of-the-art blue score. I don't know what a blue score is. That's okay. All right, we're reading the abstract here. Best thing you could do when you pick up a new paper, just look through the abstract. Okay, we don't know what a blue is. Hopefully we'll learn what that is, okay? All right, we can train on this model on 3.5 days on 8 GPUs, okay? Lightning fast, we will take that. Apparently it's better. Apparently it's better, right? Okay, we will show that the transformer generalizes well. We know what generalizes mean, right? Not overfitting. To other tasks by successfully applying it to English constituency parsing with both large and limited training data. We might not understand everything in that text, but we catch a lot of the keywords, right? Things that we all caught, right? So here are the acknowledgments. All right, let's go through some more of the paper. Now, if I was reading this, I'd be like, okay, blah, blah, blah. Let's take a look at what's going on here. Okay, let's just, I'll do a skim first to see see if I find it interesting before I move on to one of the other thousands of papers that are out there, right? Yeah, so but because we're focusing on this one, let's actually go from top to bottom here, okay? At least for a little bit. Recurrent neural networks and long-term, short-term memory, LSTM, right? And gated recurrent neural networks, oh look, all these citations if you want to learn about more of these things, have been firmly established as state-of-the-art approaches to sequence modeling and transduction problems. So, such as language modeling and machine translation. So the big one here, translating across human languages. numerous efforts continue to push the boundaries of recurrent language models and encoder-decoder architectures. Okay, here we go. We talk about recurrent models, we just talked about. Typically favor computation alongside symbol positions and input and output sequences. This is getting a little bit more complicated. All right, so what they try to do is they say, hey, there's these steps. They talk about step positions, and that's probably talking about when you have a series of words all in a row, what position are you in that row? Okay, like if you're saying, okay, this is the word that's 2 words before or 3 words before, it's starting the sequence through. Okay, and what is it talking about? It's saying that it has a sequence of hidden states, ht, as the function passes the hidden state to ht minus 1. This is literally what we were writing down for the recurrent neural network, right? Okay, and the input for position t. This inherently sequential nature precludes parallelization within training examples. They're saying, well, what that means is that if my output is dependent upon my previous output, then I can't just take each of those instances and shoot them off to different computers because they need each other. They need to talk to each other. So I can't send them off to different GPUs, different cores in the GPU for separate computation. I can't parallelize that well. Right, Angie? Yes. Yes, thank you. Angela, thank you. All right. That's what they mean. So that recurrent neural network doesn't parallelize very well because it's dependent upon, it's not like you can say this part over here will run on its own because it was dependent upon what happened in the past. Can't do it. So they're like, is there a way that we can get rid of the recurrent part of these neural networks? That's what they're talking about. Okay. Recent work has achieved significant improvements within computational efficiency through factorization tricks and conditional computation. They're talking about other methods that people have used. But now they say, let's talk right at the top, we're talking about this attention mechanisms right here, attention mechanisms. All right, attention mechanisms become an integral part of compelling sequence modeling and transduction models in various tasks, allowing for modeling of dependencies without regard to their distance in the input or output sequences. So I think what they're talking about, if we go back to our notes here, oh, here we go. The fact that in the past, like this here is in the past, xt minus 1, and this is in the future, xt plus 1. What they're saying is that it would be great is if we had a method that didn't care how far in the past we were over here, xt minus 50, right? We could still use that information in such a way that it affects over here without having this big, long sequence where all the gradients are going to be passed through. That's what they're talking about. Okay? Okay. All right. Okay. So that's what they're saying here. I'm not sure. I wish I could like highlight this with my pencil here. The fundamental constraint of sequential computation, however, remains. That's what they were talking about. The fact that the positional problem, okay, is an issue. So they're trying to solve that using this thing called attention. Okay. All right. In all but a few cases, however, such attention mechanisms are used in conjunction with a recurrent neural network. They're saying, can we get rid of the recurrent neural network? That would be great. Because then we can train things that have like words with lots of different distance apart. Again, as the example, I ate Taco Bell, so I ran to the blank. Taco Bell is pretty far back in the sequence. Imagine it's a longer sentence. Man, I was going with my friends to Taco Bell, and you would not believe what happened. Later in the day, as a result of me going there, I had to run to the toilet. Taco Bell was way further back. So we wanted to be able to see Taco Bell without having to encode all this information in our RNN. That's what they're talking about. Okay. Hope we're enjoying the Taco Bell example. It's a little embarrassing for me. All right. Okay. All right. So now they talk about the background with these extended neural GPU blocks, etc. There's a lot going on here. Let's get through what they're describing as their model architecture. The model architecture, that's what the neural network looks like. Okay, and this is what they propose. So they say our most competitive neural sequence transduction models. Sorry, we love using big words. Okay, this is a sequence model, trying to model a sequence with a neural sequence. It's a neural net. That's what they mean. Okay, have an encoder-decoder structure. Here, the encoder maps an input sequence of symbolic representations, x1 through xn, those are inputs, okay, of symbols, to a sequence of continuous representations, z, so those are numbers, okay. Given z, the decoder then generates an output sequence, etc., of symbols one element at a time. At each step of the model is auto-regressive, consuming the previously generated symbols as an input when generating the next. So it is still taking the previous symbol when it's generating the next, okay? So that's what it means by auto. The auto, it means self. Whenever you see auto, it means self. Again, we're not going to catch every detail of this from what we know in the class. But here we go. This is figure 1. Figure 1's important in a figure, in a paper. It tells you what the paper is largely about. And here we have, this is called the transformer, okay? This is what they are suggesting. And let's see what we can catch from this, okay? We got, at the bottom, we have this inputs. Those are our inputs, okay? Goes into some kind of network. Each of these little blocks are different kinds of networks or operations, okay? All right. Then we have this thing, this attention. That's one of the big parts of this paper. It's the idea of a multi-head attention. Then here we have an add and a norm. We know how to add. Yes, thank you. With norm, what do you think that stands for? Normalize. We know how to do that. Okay. Here's a feed forward neural net. That's like an MLP. That's what we've been doing most in our classes right there. Add and a norm. We know what that is. Okay. Then we go to this other attention, following this arrow along, goes to this multi-head attention, etc. An add and a norm, we know what that is. Feed forward, we know what that is. Add and a norm, we know what that is. This is a linear activation layer for a neural network. This is a softmax. We use that for one of our examples. I'm pretty sure the actor-critic model, and it comes out with some probabilities. Okay, there's a lot going on here, but the biggest thing that's a little confusing right now is this multi-head attention, which we have not defined. That's, they say, is new in this paper, okay? This in positional encoding, we can ignore that for now, but that's more or less saying, where are we looking back in time in our sequence, okay, of words? Where is Taco Bell, as we will put it, okay? All right, so, all right, we have this encoder and a decoder. Let's kind of skip through a little bit. Let's get to the attention part here. I want to get to that attention. What's going on? Here we go. This is a figure. Figure 2, this is a very compact paper. It says, hey, figure 1 is what the whole thing looks like. Figure 2 is what these little components look like. All right. On the right, I see that multi-head attention. Okay, this is what it looks like here. Okay, inside is that thing they call a scaled dot product attention. All right. In goes these V, K, and Q. What are those? We'll figure it out. One step at a time. It goes into some kind of linear layer, which go into this scaled dot product attention, whatever that is, okay? Good news is it's off to the left. It's over there, okay? Then we concatenate them together. That's what concat means. We concatenate, whatever's happening, they're putting them together, like we're smushing them together. Then you have a linear layer, and that's the output, okay? So, but clearly, this is an important thing. This little H, this little hidden layer area with this dot product attention. Well, that's off to the left. Scaled dot product attention. Takes in 3 things, some Q, some K, and some V. What those are, I'm still not sure. Okay, we'll deal with it later. Okay? Takes in a matmole. Anyone know what a matmole is? Matrix multiplication. We know what that is, right? Then we do some scaling. Okay, scale things, you know, maybe a normalization type operation. Some kind of masking, which is optional, which basically means ignore some stuff. Ignore some stuff that you don't care about. But it says it's optional. I'm assuming that opt is optional, right? Then we throw it through a softmax, which is a sort of activation type thing, you know, like which more or less takes the maximum of a bunch of operations, okay? And another matmole. They're like, hey, we had this idea. Why? It's not fully clear from what we've read so far, but it's clearly there's a whole history of attention, and they create this thing called multi-head attention, all right? Okay, left is the scaled dot product attention, and the multi-head attention consists of several attention layers running in parallel. Oh, okay. See that little ghost, the little ghosts of things in parallel? Yeah, multiple of them. Like a multi-head attention. You can see like the little, you see like the ghostification behind it? It's 3D, it's very fancy, okay? We live in the future. Look at that, okay? It talks about it. We call our particular attention scaled dot product attention. The input consists of queries and keys. Oh, Q is queries. Like maybe a question or things that are going in. And keys, well, we can go back to keys and we figure out, we can go back and see what they're talking about with keys, right? And of dimension dk and values of dimension dv. They're giving you dimension. That basically means how many are in the list. Okay, we're talking about dimensionality, like how many are in the list, how big is the vector, okay? We compute the dot products, remember that from calc whatever, okay? And with all these keys, it's getting a little complicated, but they said, hey, here is this computation, that we have this thing called attention, and it's equal to the softmax of all this. And what is this more or less doing? It seems to be doing is it's saying, hey, of all of the stuff that's coming in a list of possible queries, possible inputs, what's the thing we should be paying attention to? Okay? Pay attention to Taco Bell. Okay? That's an important indicator of what the next word's going to be. Okay? That's going to have to be encoded somehow as attention. All right? All right. So they created this scalable thing. We have multiple attention heads that seemingly can be parallelized. All right? It's getting a little complicated, but I'm just trying to follow the gist here. All right? All right? Okay? And they said, okay, we're going to use this multi-head attention. Well, there's some details here. We can go back if we find that important. All right? Instead of performing a single attention function, we found it's beneficial to linearly project the queries, keys, and values h times with different linear projections to d blah, 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 blah. We found by trial and error this works if you do lots of times. Okay? We figured that out. So this multi-attention head says, hey, let's put together, let's concatenate the attention from each of those little attention networks, okay? All right? Let's put them all together. What are all the things that we care about? All right? So let's skip ahead a little bit. Okay, this is getting a little dense. Okay? There's some feed-forward neural networks we saw. Okay? Hey, notice little weights and biases popping in. We've seen those before. Those look familiar, the weights and the biases. You multiply by a weight, you add a bias. Feed for FFN, that's feed-forward neural network. What's their activation function? Array loop. Things we're recognizing, things we recognize. It's getting a little dense. Okay? Talking about softmax and embeddings. All right, there's some stuff going on. And here they talk about, this is why they think that their method is good. Okay? They talk about their methods, attention, self-attention versus recurrent and convolutional methods. And these are the complexities. So this talks about like, oh, the complexity of us searching along a grid with this n by n, if you want to search the whole grid, would be n squared. This little O, that's called a O count, a big O notation, how complex it is. So n squared would be, you know, that at worst, you got to search over n squared different possibilities, n squared different iterations. And they argue that their self-attention is more efficient, okay? For reasons we won't get to, let's get to positional encoding. Let's get past that. Let's skip past that. Does it work does it work well? Does it work? What does it work? Does it work, my friends? Okay? Okay, look at their model. There's the transformer. There's the base. And it looks like they have bigger numbers for BLEU, which is, I think, a performance metric if we search for it. If she's better BLEU score. Oh, that means probably big is good. Score is probably big is good. They're bolded ones, they're better. And their training cost in floating point operations, or flops, is less by multiple orders of magnitude. 10 to the 18th, 10 to the 19th on the bottom there. Oh, it's better. How nice. Okay? That seems to be working pretty well. Let's scroll back, by the way. Just look at a few buzzwords. Regularization. We talked about that. We had a whole lecture on regularization. They talked about specifically something called label smoothing and residual dropout. That's what they apply as a regularization to prevent overfitting. Okay? What optimizer did they use? Atom. Beta 1, they give you the beta 1, beta 2, and epsilon. Same things that we put into our atom optimizer, if you remember that, right? Okay? Real things that we coded from scratch. Okay? Here's the hardware. They used 8 big GPUs. We were able to train it for a while, okay, for 3.5 days. Okay? Oh, look, training data and batching. They showed this is how they chose their training data. They had 4.5 million sentences. That was their data. So we're hopefully learning the tools that we had to read through a paper like this when we get through the end. Okay? All right, they talk about model variations. Oh, look, there's more data. Okay. They found that it's really good at parsing English. Pretty neat. Pretty neat. And it's got scores here that it's trying to perform against. Okay? So, in conclusions, in this work, we present the transformer, the first sequence transduction model based entirely on attention, meaning it doesn't need recurrence. Okay? Attention is all you need, you might say, according to them, right? And it goes on. Let's get to the end here. Does anyone know why I showed this paper? Anybody know? This is actually a very influential paper. This thing up here, called the transformer. Where is it? Figure 1. Transformer. Anyone heard of ChatGPT before? What does the T stand for? Transformer. This is the invention of ChatGPT. Several years before ChatGPT was released. This was like more or less, it was turned into the 1.0. This was the key innovation, was its ability to scale and be able to train across a lot more data more efficiently. Okay, you take in a ton of data and be able to predict a sequence. In what case? Text. Anyone who's used one of these large language models like a ChatGPT, you'll notice that it doesn't give you just the entire answer all at once. You see it's like literally word, 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 word. I mean, that's just how it looks. But like it is literally saying, it predicts the first word, which is a response to your question. Okay? The input. That's your prompt. Okay? All right? And then it spits out the probabilities that a certain word is the next word in the response. Okay? You can ask it, what is the airspeed velocity of an unladen swallow? Like, then it will try to predict what's the first word of the response. Okay, based on that, what's now the second word of the response? All the way until it eventually hits the termination condition that says done. Okay? So this is the invention of the transformer, which is the core of all of this current, like generative, so much of the generative modeling that we do back in 2017. Okay? All right? These people went on to be pretty famous in the field. Published this paper. And no doubt, there are elements of this that don't make perfect sense, top to bottom, based upon one intro to machine learning course. But you can see the components, right? The things that we learn throughout the course that play into this. The training, the regularization, what's your loss function, what's the loss function, what's a encoder, what's a decoder, what's a feed-forward neural network, that's all in there. So you now at least have some of the tools to read some of these, hear some of this recent news about machine learning, and look at the papers that come out recently about it, and interpret those. Okay? And that's what I hope you get at least some of that from this course, even though you're not going to get everything here, but at least it gives you some basis to move forward and experiment on your own for how to use machine learning, and maybe go on to further courses that really dive more deeply into different subsets of machine learning. And so for that, I've also, as sort of a closing note, since this is the last, in the last lecture a formal lecture we're going to do in the course, I want to thank you all so very much for being a part of the class. I had a lot of fun teaching it, a lot of fun working with you all. Hope you learned a couple of things, and also hopefully learned that you can code this stuff up too, because we did it ourselves in class. So I want to thank you all, and I hope you have a wonderful, wonderful rest of the semester. Take care.